let us proceed with the third subtopic, electric potential. At the end of this session, you should be able to define electric potential, equipotential lines, and use the equation of electric potential. And we want to calculate the potential difference, delta V, deduce the change in potential energy, delta U, and lastly, to calculate the potential energy U for a system of point charges. Electric potential is defined as the work done per unit charge to bring a test charge from infinity to a point and electric field produced by a point charge. So we have a point charge and we want to bring a test charge from infinity to a point in electric field. So the work done to bring this charge to this point divided by the magnitude of charge is equal to electric potential. The unit for electric potential is joule per coulomb or volt. Let us explore more about the electric potential. Imagine we have a situation. This is Ali. So imagine Ali wants to push this test charge towards a point charge. So when he pushed the test charge towards the point charge, Ali is actually doing work. So when the test charge is moving to the point charge, this test charge is actually against the repulsive force between these two charges. So when Ali is doing work, his charge is actually against electric potential energy. Electric potential is defined as the electric potential energy at a point in an electric field. So, in explanation, sebenarnya kalau kita nak tahu nilai electric potential at this point, as this point is actually in the region of electric field of this point charge, the electric potential at this point is actually telling us the amount of electric potential energy which is equal to the work done by Ali per unit test charge at this point. So that is the meaning of electric potential. The other concept for electric potential is equipotential lines or surfaces. So for this term, we have its definition. It means that in one line of equipotential that is always drawn as dotted line, all points at these lines are having the same electric potential. So let's say we have point A and point B. So potential A is equal to potential B. So when these two potentials are equal, meaning the electric potential difference is 0 because VA is equal to VB. So VA minus VB is equal to 0, which means there will be no work done as the work done is equal to delta V. So since our delta V is equal to 0, so the whole work done will be 0. These equipotential lines is normally drawn as dotted line and it must be perpendicular to the electric field lines. So let's say this is your electric field lines. So we must draw our equipotential lines perpendicular to the electric field lines. So this is our equipotential lines. Based on the given condition, so for an isolated charge, this blue dotted line here is our equipotential lines. And this orange line here is the electric field lines. So you can see here that these two lines are perpendicular to each other at any point. For uniform electric field, this is the lines of electric field. And the dotted blue line here is the equipotential lines that is always perpendicular to each other at any point in the uniform electric field. So this is our equipotential lines. Now we want to deduce the term or the equation for electric potential at a point charge. So the basic equation, please recall, we have looked at V is equal to work done or the electric potential energy per unit charge. So to get the equation for electric potential energy, we have to know the work done. Here is how we deduce the term for the work done by the external force if we want to bring a test charge from point A to point B. So it is undergoing the process of integration from point A to point B. From the term of the work done we have got earlier, then we can have the term for the electric potential energy, that is U is equal to KQQ over R. This is the definition for potential energy. It is equal to the work done to bring a unit positive charge from infinity to a point. So electric potential is equal to electric potential energy per unit charge. So we take the equation that we have got before and divided by the test charge, and finally we have the other term for electric potential, that is KQ over R. So for your information, for electric potential, it must consider the sign of charge. And electric potential is a scalar quantity, means it has no direction. So you will never draw any direction for electric potential. And so does the electric potential energy. Both of these has no direction. So to determine the electric potential for a system of charges, which means a system that has more than one charge, we just do the calculation. There will be no direction drawing or sketching, so we just do the calculation. So for this case, for example, we have Q1, Q2. So Q1 will produce its own potential. Q2 also will produce its own potential. So this is the distance between the point P and the charge R2. This is the distance point P to Q1 R1. So to calculate the electric potential at point P, it is actually electric potential due to charge number 1 at point P plus electric potential due to charge number 2 at point P. So electric potential is KQ1 over R1 plus KQ2 over R2. So this is how we do the calculation. For the second example, if we have 3 charges, meaning you have to add up all the potentials that is possessed by these 3 charges. So potential at point P is going to be potential due to charge number 1 plus potential due to charge number 2 plus potential due to charge number 3. So the thing that you have to be more careful is at the distance. So it's going to be R3, this is going to be R1, and this is going to be your R2. So to get the magnitude of electric potential difference, the concept is the V final, electric potential at final point, minus the electric potential initial. So in this case, we are going to bring our charge from point B to point A. So point A is going to be the electric potential final and point B is going to be electric potential initial. So this is the equation. Or, apart from this equation, you can also use delta V is equal to the work done per unit test charge. And we also have the term for change in electric potential energy, delta U. So delta U is equal to UA minus UB, or U final minus U initial. Remember, we have U is equal to QB, that is coming from V is equal to U over Q. that we have learned previously. So U is equal to QV, and here we can have QVA minus VB, and it is equal to U is equal to Q delta V, potential difference. And for the electric potential, you have to consider the sign of charge to include in the calculation. For a system of charges, which means a system that has more than one charge, one point charge, the electric potential energy is to add up all the interaction between the charges. So for example, in this case, we have three charges, Q1, Q2, Q3. So in this system, we can see that there are interactions between Q1 and Q3. So it's going to be U13. Interaction between Q2 and Q3. So there is a potential energy U23. And also we have interaction between Q2 and Q1. So for this interaction, there will be an electric potential energy of U12. So for this system, we are having three electric potential energy, and we are adding up all the terms and all the potential energies. So this is how we calculate the electric potential energy for a system of charges. And again, the sign of charge must be substituted in the calculation.